Okay, welcome everybody. So today, hopefully, this is going to be the last day for Auslander-Reiten theory. Tomorrow we will, I plan to talk about representation types, yeah, and say something about it. So we have been looking at the concept of an Auslander-Reiten sequence, yeah, and this is an exact sequence which is not split, but it is the best amongst the non-split sequences. Yeah, and we have to make that concept formal. And so in order to make that precise, what we have started doing is look at left minimal and left almost split sequences. So left almost split is precisely what we want to capture. It means that it is not a split morphism, but if it is not a split, if there is any morphism which is not a split mono, then it factors through this morphism. So it has a universal property amongst the morphisms which are not split. Yeah, so it is the best in that sense. However, such left almost split morphisms are not necessarily unique. Yeah. So therefore, we also added one more condition, namely left minimality. Yeah, which means if it fixes an endomorph, if some endomorphism fixes the image, then at pointwise, then image of f pointwise, then actually it is an automorphism. Yeah, we looked at this particular definition last time, and so we are going to go ahead from that place. We saw that left minimal almost split maps with a fixed target, fixed source, they are unique. And the domain of such morphisms is actually indecomposable. So we looked at these two simple proofs and we looked at some examples. And we also looked at some characterization of irreducibility that concludes that whenever we have an irreducible monomorphism, then its co-kernel is indecomposable. Okay, so we covered so much material already so far. So any questions about this? Anything that you would like to say? Okay, in case there are no questions, then let us see how left minimal almost split morphisms are important. Well, first of all, this theorem says that they are irreducible. So we have got like if you know left minimal almost split morphisms, then you have got a large supply of irreducible morphisms. Moreover, yeah, the second condition is actually very interesting. So if at all there is some irreducible morphism with domain L, then actually you can sum it up on the codomain side with another irreducible morphism such that it becomes F. Okay, so basically the target of a left minimal almost split morphism, that target can be broken down into two pieces. One of them could be 0 if needed, but it can be broken into two pieces such that one is the required given M dash and the other one is M double dash, and this morphism can be, this is isomorphic to our given left minimal almost split morphism. So this very strong uniqueness property, yeah, this is what makes these morphisms special. So right now, what I'm telling you is that if you are given some L which is indecomposable, then the knowledge of a left minimal almost split morphism with that domain implies that you know all possible irreducible morphisms. Yeah, so let me write something. So what are all possible irreducible morphisms in this case? So all irreducibles with domain L are of this form. So L to M, which is the given left minimal almost split morphism, and then some split map. Yeah, so this is split, composed with any split morphism where M dash is non-zero. So we have a very good understanding of all the irreducible morphisms. Of course, up to isomorphism, yeah. So in terms of these properties, now we are ready to define what an Auslander-Reiten sequence or an almost split sequence is. It is a sequence of the form 0, L, M, N, 0, where the morphism from L to M is left minimal almost split, and the morphism from M to N is right minimal almost split. So we are simply putting these two together. Yeah, of course, right now we are not saying anything about their existence, but this is just a definition. So, of course, because left minimal almost split implies left almost split, which means it is not a split mono. So therefore, an Auslander-Reiten sequence is never a split sequence. Okay. And if L is not injective and N is not projective, yeah, that also we can easily show. And no, I don't think easily. Yeah, I shouldn't say that. Oh, no, sorry. It's easy because if L were injective, then this the morphism F would become split. That is the definition of an injective morphism. So therefore, L is never injective and N is never surjective. N is never projective. So you might connect it with the Auslander-Reiten translate. Yeah, that we don't want the last one to be projective and the first one to be injective. So tau M is equal to 0 whenever M is projective. Yeah, hopefully you remember that. We saw that if and only if condition. And two AR sequences, yeah, I mean, they are isomorphic. I mean, what do we mean by isomorphic? Like there are vertical morphisms between these two short exact sequences. So they are isomorphic if and only if either they are isomorphic in the first term, if and only if they are isomorphic in their last term. So basically what this tells us is that any one term of this sequence uniquely determines the entire sequence. Any one term, I should be more precise. Yeah, what I mean is either the first term or the last term uniquely determines the Auslander-Reiten sequence. Any questions so far?
So the middle term does not?
Middle term doesn't determine that. Yeah, so either the first one or the last one that determines. I'm not sure about the middle term. I mean, I can't give you an example. I can't even think of an example where the middle term is same. Most likely it won't be same, but we are only talking about the endpoints. Okay. So there are equivalent criteria. Of course, I mean, this is a very strong condition, so we don't have to talk about so many things like these two things simultaneously, like left minimal almost split and right minimal almost split. So equivalent criterion says that L is indecomposable and G is right almost split. That is sufficient. See, we are dropping the minimality, right minimality on G. We are just saying right almost split and L is indecomposable. So it is the kernel of a right almost split thing. And G is right minimal almost split. That is also sufficient. We don't even need the symmetric version. and L and N are indecomposable and both of them are irreducible. Both morphisms are irreducible. That is enough as well. So the only way you can put two things like the composition of two irreducible morphisms is zero. What is that condition? That, well, the domain and codomain, if domain and codomain of the entire composition is indecomposable, then that is a unique possibility. Yeah, it has to be an AR sequence. I mean, yeah, maybe I said only composition is zero, but yeah, exactness. One irreducible morphism is a kernel of another. So that implies this. So these such sequences, if they exist, then they are really good. But how to guarantee their existence? So in fact, just look at this note 2, that L is not injective. So given any non-injective, does there exist an AR sequence which starts at L? And given any non-projective module, does there exist an AR sequence which ends at that module? So we are going to answer this question today positively. I mean, that is the main purpose of what we introduced earlier. Yeah, the Auslander-Reiten translate. So we'll determine that. Okay, so at this point, because many of the participants, as I realized in the first week, they are not familiar with homological algebra. So I have been doing a primer on homological algebra, and the next thing in that list is these Ext groups. So Extends are actually so-called derived functors of the home functor. Let me try to make this idea precise, and this is actually a very interesting concept by itself. So suppose you are given two abelian categories and a left exact functor between them. So if we are given an exact sequence 0, x, y, z, 0, then we get 0, fx, fy, fz in D. But we don't have the last term. Last 0 is usually missing. Unless we know that, I mean, we have seen that if we are talking about home P blank, then we will get a last 0. But otherwise, this last thing is missing. So if we desire to extend this exact sequence on the right side, how are we going to do it? The natural thing, the answer that we will provide here, yeah, we don't want to do too much of homological algebra. The simple answer we'll provide is for the home functor. Yeah. So far, I think I have been writing that home M blank is a functor from A mod to abelian groups, which is correct. But because we are talking about finite dimensional K algebras, it is also a vector space, K vector space. So I can write K mod here as well. Okay. So how to do this? Yeah. So suppose we start with a projective resolution of M. Yeah, we want to compute the derived functors of this f, this home M blank functor. This is a covariant functor. So we start with a projective resolution. Recall that in a projective resolution, we do not have M. Yeah, we always drop that M. This sequence is not exact, and we can recover M as the zeroth homology of this complex. Zeroth homology, I mean, here I'm going to talk about homology and cohomology. So in simple words, the nicest thing is an exact sequence. But if a chain complex is not exact, which means the composition of any two consecutive things is 0, but the sequence is not exact, then we have to measure the failure of exactness at a particular point. So normally what we do is, well, if it is exact, then the image of the previous map is equal to kernel of the next map. But when composition is 0, then image only sits inside the kernel. Yeah, not the other way around. The other way, inclusion doesn't necessarily happen. So kernel modulo image is the measure of failure of exactness, which is the so-called homology or cohomology depending on your indexing. Okay, so the zeroth homology of this projective resolution will give us M back. And we are starting with an arbitrary one. Yeah, arbitrary projective resolution. I'm not necessarily talking about the minimal one at this point. And then from this, we can construct for any n a co-chain complex. See, chain complex, co-chain complex, these names are relative to the indices. Yeah, there is no real difference between them. But if the indices in the chain complex, the indices are decreasing, whereas in a co-chain complex, the indices are increasing. That's the only real difference. So here you can see we are always writing P2, P1, P0. And for injective resolutions, it's always I0, I1, I2. Yeah, the indices are increasing. Okay, so we can construct a cochain complex, which we denote by home P dot comma N. So what we are doing is 0 to home P0 N because it's a covariant functor. So sorry, in the first component, it is contravariant, and therefore we are taking home P0N, home P1N, home P2N, and so on and so forth. The induced maps, F1 star, F2 star, etc. What are those maps? Well, they are simply the composition with F1. Yeah, if you have a map from P0 to N, then you pre-compose it with F1, you will get a map from P1 to N, and so on. Okay. So the X group, XNMN, is defined to be the kernel modulo image. Yeah, very simple. Kernel modulo image of this. Kernel of Fn plus 1 star divided by, quotiented out by image of Fn star. So this will be an abelian group or a vector space in this case. Yeah, that's all. Any questions? This is the so-called nth cohomology of this cochain complex. Okay, just to gauge something, like how many of you already know about X functors? Can you please raise your hands? Okay. 3. Okay. 3, 4, 5, 6. Okay. Thanks. So I'm doing the correct thing by talking about this. Only 6 people out of 29 know about it. So I should, I'm hopefully teaching you something. Even if you don't remember anything from Auslander-Reiten theory, you will at least remember this. Okay, so nth cohomology of this particular cochain complex is the nth extension group. And well, you might ask, yeah, we made a random choice of this projective resolution. So shouldn't it depend on the choice of the projective resolution? The answer is no. Yeah, because this is a homotopy invariant, chain homotopy invariant, and projective resolutions are unique up to chain homotopy. Like you might have, if you have done a course on algebraic topology, then one common phrase to remember is homology is homotopy invariant. So same thing applies here as well. So it is independent of the choice of the projective resolution and balancing. You can compute the nth extension group also using the injective resolution of n instead of a projective resolution of m. Do you understand? Like you just take an injective resolution, you compose, you take home m blank on that, and then you compute the nth cohomology. This will again be the same. The proof is complicated. We are not doing any proofs anyway, and uses spectral sequences. And the main advantage of doing this whole thing, which is like answering this question, can we extend this exact sequence on the right? The answer is yes. Now we can do it in this fashion. For home m blank, we can say 0, like home mx, home my, home mz, then x1 mx, x1 my, x1 mz, and so on and so forth. These long arrows that I have drawn, they are known as snake arrows, and the proof comes from snake lemma, which is again a very celebrated result because of its name in homological algebra, celebrated and basic result. So this actually prompts you to ask another question. Yeah, I have written x1, x2, and so on. So is home really x0? And the answer is yes. Yeah, home is indeed just x0. You can prove all those things. Any questions on this part of homological algebra? Okay, so just remember that the X groups, I mean, they are just vector spaces, just like home. They are no longer modules. We are just talking about abelian groups. Okay. Actually, yeah, I mean, for this, you can deduce something about the projective dimension. So if xm is non-zero, but xm plus 1 is 0, then that is a characterization of projective dimension of that module m to be little m. Yeah, similarly, you can talk about injective dimension. These things are important. I mean, they are also interesting because then projective dimension of any module is at most 1, which means that x2 onwards everything is going to be 0. So in the case of hereditary algebra, the x2 onwards everything is 0. So this last map, x1 my to x1 mz, that is actually surjective in that case. Okay. So there is an alternate description of the x1 group. Well, it is in terms of short exact sequences. So this is actually quite surprising. Yeah. So you just look at an extension of n by m. So extension of n by m is just a short exact sequence. And two such short exact sequences are said to be equivalent if there is a commutative diagram like this. Okay. So n equal to n, m equal to m, and in the middle, e and e dash, there is an isomorphism which commutes with the diagram. Yeah, so that commutation property is really important. So this is just the definition of an extension of n by m. And actually, we can add two extensions. So the collection of all these extensions forms an abelian group. Okay. So here is something about how to add. Yeah, if we are given EI, FI, GI, like even if F1, G1 and E2, F2, G2 as two different extensions, then we have what we do. Yeah, I mean, maybe last time I gave you one proof. The purpose of that proof was to talk about pullbacks in particular. So let me just quickly go back to that place. It was just pages ago. Yes, okay. So this was the pullback, yeah, in black. So we were given m to n and x to n, these two morphisms. Then we constructed the pullback, which was x cross m. This is a fiber product over n, and we just said that these are elements in the product of x and m, such that their images under h and m agree. So this is the pullback. Dually, what you could have done is, if you were given these maps, so let's say L to this and L to this, then you could have defined a push out. Yeah, push out is take a direct sum and then quotient out by something. It is exactly the dual thing. So pullback and pushouts are important categorical constructions. They are an example, one examples of limit and co-limit each. So what I am trying to say here, the addition of these two short exact sequences implies a combination of both of them together. So we start with a pullback and followed by a push out construction. And together they construct an abelian group. And these are just the induced maps which we get from universal properties of pullback and push out. And the surprising thing is that the group of extensions of n by m is actually isomorphic to the group x1 mn. Okay, so this, whatever this abelian group was, that is isomorphic to the group of extensions, which is a very surprising fact. So it has an alternate description. Now, why have two different descriptions for the same group? Well, for our purposes, we want to study Auslander-Reiten sequences. So they are almost split sequences. So they will give you one particular element of the group of extensions. On the other hand, the homological description will tell you where that X1 group will fit in the long exact sequence. So it's a twofold purpose, so therefore two different descriptions. Okay. So what is the role of split extension? Yeah, we said that it was the best possible exact sequence. So the split extension will give you the zero element of this group of extensions. It's always there. So it is the trivial element. Okay. So any questions about this? Okay. So let us look at one example. Yeah, I have left some gaps over here. I mean, I don't expect you to immediately understand what pullbacks and pushouts are, but I will hopefully try to convince you that this is the right thing to do. So we are talking about Kronecker-Quiver. We have been talking about Kronecker-Quiver quite a lot. So let M be the simple module at vertex 1, M be the simple module at vertex 2. So this is S1, this is S2, and there is one extension. What is the extension? You only take identity arrow corresponding to alpha in one of them and identity arrow corresponding to beta in the other one. Of course, with any short exact sequence, you can first verify whether the dimensions agree. The dimension vector of this plus the dimension vector of this is actually equal to the dimension vector of this. Now tell me, what is the split exact sequence if you are given S2 and S1? The dimension vector will still be 1, 1. But what is that representation in the middle? Anyone? Come on,
It's
this is
0, 0,
simple.
right?
No, what 0, 0?
And both the maps are 0, 0 from K to K.
Okay, right. Yeah. So
Because
0,
it's
0
a direct
maps.
sum of two maps.
Yes, correct. Both maps are 0. That's exactly right. Yeah. So, however, these are non-split extensions. You can immediately see that. We are actually connecting those two dots with the help of an arrow, with the help of an identity arrow. So this is non-split. Then second one is also non-split. And obviously, because the location of alpha and beta matters, we are these two are not isomorphic to each other or even equivalent to each other. There will exist, there can't exist any isomorphism between them. Okay, so what is the pullback of these two? So you are given G1 and G2, so what is the pullback? Well, pullback precisely consists of those pairs of pairs such that G1 of lambda 1 lambda 2 is equal to G2 of lambda 2, mu 1 mu 2. So are you convinced that this one is just going to be? So observe, yeah, what's happening. We have dimension vector here is 2, dimension vector is 2. So sorry, dimension vector is 2 comma 2 in E1 cross E2. And we have one relation over here. So the dimension vector will reduce by 1 in the first component, because the second component is 0 anyway. So only in the first component, the dimension vector will reduce by 1. So that will be k square, and then you are identifying this map is going to be your first inclusion. So it is a 2 cross 1 matrix. So 1 0, and this will be 0 1. So see, while taking pullback, what happened? We actually joined those two entries. We joined E1 and E2. We joined the first vertex of E1 and E2. Yeah, that's all happened while taking pullback. Whereas now we have to also take a further quotient by this set. So we have to identify the images of F1 and F2, image of F1 and F2 in this pair. Well, those pairs all only look like 0 comma eta and minus 0 comma eta. Yeah, there is nothing else happening. So actually the final result would be this, that we will have kk. This one will be 1, this one will be minus 1, and this is the so-called band module. Okay, so therefore we get this particular sequence. 1 and minus 1. Yeah, in fact, you can have 1 and lambda, but for every lambda, they are pairwise non-isomorphic. Any question related to this? Like, did you understand the computation?
As far as I can see, you get 1 1, not 1 minus 1.
No, there is a minus sign here. So you have to identify it with the opposite.
Yeah, so F1 would be 1 0 and F2 would be 0 1, right? So when we take minus F2, then it becomes 1 minus 1 is killed, which leaves 1 1.
F1 would be what?
If we just take the pullback, I think F1 would be the map 1 0.
Uh-huh. Just hold
Okay,
on.
well, rather
Pullback is F1 would be 1 0, and you are saying this is 0 1 or 0 minus 1. Are you talking about this one or this, like while quotienting out the pullback by this relation?
let's say we look at F1 comma minus F2 as a map from N to the pullback.
Yes.
I think that would be 1 minus 1, right?
Yes, that is 1 minus 1. Yeah.
But then we're killing the 1 minus 1 subspace of k squared.
Maybe am I making a mistake here? Is this 0 1? Yeah, I think this is 0 1. This shouldn't really matter. In the pullback also, we have to introduce one negative sign somewhere. Yeah, I'm not getting that part. Maybe because the pullback means the square has to commute. Oh no, it just has to commute. Yeah, nothing is cancelling. It's not the co-kernel. Well, I mean, the same example was computed in a book also. So maybe there is some problem with the convention. I'm not doing it from my own computation. So let us just accept it for what it is right now. Yeah. Even if it is 1, 1 or 1 minus 1, it's something where you get a band module. Okay. So this is the group of extensions, and we are going to use that group of extensions in a pivotal construction over here. Yeah, and pivotal theorem, which will guarantee the existence of Auslander-Reiten sequences. Okay, so these are the so-called Auslander-Reiten formulas. So given any two modules, we have isomorphisms between X1 Mn. So you can calculate the group of extensions in terms of the homes in the projectively stable and the injectively stable categories. Okay, so D lower home, if you remember, lower home means projectively stable category, tau inverse n comma m, and D upper home is injectively stable category, and then you apply the duality and you get this. So, and moreover, this particular isomorphism, this particular pair of isomorphisms is natural in both components. Let me quickly remind you what we were doing yesterday, if in case you have forgotten what these things are. So we observed that tau annihilates projectives. So therefore, in general, tau inverse tau m is not isomorphic to m. So tau is not an equivalence. So we sought out to get an equivalence, get an induced equivalence via some quotients of our regular categories. Now, in order to construct a quotient, we have to have a two-sided ideal. And if we use the ideal of morphisms which factor through a projective, then we get the so-called projectively stable category. And dually, if we use the ideal of morphisms factoring through injectives, then we get the injectively stable category. So that we have a perfect equivalence between the projectively stable and injectively stable categories induced by tau and tau inverse. Okay, so this is the home that I'm talking about while discussing this. Yeah. So Auslander-Reiten formulas, I mean, see, normally computing X1 groups, it's really hard. Yeah? However, because of these formulas, things become really simple. You just have to calculate certain home sets rather than computing X1 groups. Okay. All right. So we are going to look at some tensor products, again, part of our agreement that we'll do everything from scratch. So tensor products in this case, and also, I mean, I feel this is also important because there are some people in the audience who have only seen commutative algebra. For them, tensor product just takes pair of modules into a module. Yeah, but here it's just an abelian group. So we have to set up the left and right thing correctly. So tensor product is a bifunctor, covariant bifunctor from mod A cross A mod to AB to the category of abelian groups. And for writing down the home tensor adjunction, we need a BA bimodule, YBA. So what does this YBA do? Well, tensor with that bimodule gives you a functor from A mod to B mod. And home with that bimodule gives you a functor in the reverse direction. The home is the right adjoint and tensor is the left adjoint. Well, if you don't understand language of adjoints, then you should try to understand this. Yeah, that given any left A module X and any left B module Z, home Y tensor X comma Z is isomorphic to home X comma home YZ. In fact, I mean, in many situations, people start talking about adjunctions via this particular isomorphism, which is again natural in both components if you understand what naturality means. Okay. So let us look at the proof of these AR formulas. Yeah, there are two AR formulas. Of course, you can see X1 is isomorphic to this lower one is what we are going to prove. And this will do here live. And I did not write it on purpose. Okay, so the first thing we'll need is a lemma. So suppose, so for L and M in A mod, the group homomorphism, yeah, this is just a group homomorphism, not a module homomorphism, which is phi L M from home A L A tensor over A M to home A L M. So what we are doing, we are taking a morphism, then we are taking a simple tensor with some element, and we are mapping this pair to another homomorphism, which takes L to the only thing that you can do. Well, if you apply F on that, then you will get to FL, and FL is a scalar which acts on M on the left, because M is a left A module. The group homomorphism, yeah, which is defined this way. Satisfies the following, has the following properties, yeah. I'm not going to prove everything, but at least we'll see some use of home tensor adjunction. The first property is that if M is projective, then phi LM is an isomorphism. Okay, so let us try to prove this. So home A LA tensor A with M. Well, if it is projective, it is sufficient to show it for an indecomposable projective. Yeah? And we are only talking about finite dimensional indecomposables. So here actually I'm trying to tell you one technique that Upendra introduced to me the other day. So every projective module can be written as AE, yeah, for some idempotent E. Indecomposable projective means E is primitive idempotent. So let us take an isomorphism with this. Well, this whole thing, we are just taking tensor with something. So it is home LA tensor A, and then this whole module is acting on E. This whole thing is acting on. We can take this E out of this. Yeah, basically. And then this is isomorphic to A is always with respect to tensor product and home. The ring or algebra itself is identity. Right? So this is just home A, LA. You can actually prove these things very easily as well. And then E is just outside, which is nothing but home A, L, and we can take this inside. There are several things here, but hopefully not a difficult one. Okay, so this is the first property that we need. And second one, which I'm not going to write, I'm not going to give a proof of. But I mean, once you look at this particular Auslander-Reiten formula, then the natural question you ask, yeah, how exactly am I going to get hold of this home set in this category, yeah, in this projectively stable category? It's not natural, yeah, by like quotienting out by project morphisms factoring through projectives. So actually, then the important piece of the puzzle is that co-kernel of phi LM is actually equal to the projectively stable home of LM. Okay. And moreover, like this is natural. The third one is that phi LM is natural in L. And I'm just writing this naturality condition for people who do care about categories, so they can appreciate what is happening. So the second property is really the most important one here, that co-kernel of a certain map is this particular projectively stable home. That will, and property 1 will also be used. Okay. Now we have this particular morphism. Let me just keep it in view. And I'm going to apply D on this. Okay, so observe that if I apply D, okay, sorry, maybe I should ask this. People are not participating actively. So if I apply D on this particular morphism, then what will I get? What will be the domain? Just a simple question. What's going to be the domain? D is a duality. Yeah. Anybody, please? Okay. Well, I hope that you are following. Even if you are not answering, hopefully you are following. So D will actually change the domain and the position of domain and codomain. Yeah. So we will have D home ALM, and then I will have D phi LM. And then I will have D of this home A LA tensor over M. Yeah, hopefully you understand that this is contravariant. So we have changed the direction. Well, what is this though? D is nothing but home K, blank K. So home K, then home A, LA, tensor M over A, comma K. Well, now let us use the home tensor adjunction so that we get home K, home A, LA as it is, and we transfer this M to the other side. Well, that means home MK. But what is home MK? It is just DM. Yeah, do you agree that it's just DM? Okay. Then, well, any module is its double dual. Okay, so therefore, this is actually isomorphic to home K. I mean, this is D square. Yeah. D home LA. DM. I haven't changed anything so far. But I can take out one D and then revert the home. outside. Yeah? So inside. So I will get D home A LA. Okay, can anybody recognize what the right-hand side is? Right-hand side of the last home is? No? Okay. This is just equal to, yeah, home M new L. Are you okay with this? Oh, sorry. I think
sorry, there is one thing that's confusing me here.
Uh-huh.
On the left side of the second line,
Uh-huh.
on the very outside, you've written home K, but I think that needs to be home A.
Yes, it should be home A. Yeah, I was just looking at that and I thought that I'm making some mistake over here. Yes, so that's correct. It's home A because I have already utilized, when I transferred it to the other side, I have utilized home K. Yeah, this should be just A. Thanks.
But then
Yeah,
how does the isomorphism on the third line follow?
Oh, wait. Let me check the source. Yeah, I shouldn't make a mistake while talking. Hopefully the authors are also making this thing clear. The inside thing should be just from duality, isn't it? I mean, this is just the left modules or right modules thing. This isomorphism is what you are talking about, right?
Yes.
If it were home K, then I think that would be more clear, but maybe for finite dimensional algebras, this is also true. Yeah, how to prove that home blank K and home blank K. We just have to evaluate. I think it should follow from Yoneda. Because all of them are home functors. So representable in the first component or second component, that should tell you the right thing. Yeah, it follows from Yoneda. So this whole composition is what we are interested in right now. Yeah, so see, somehow through this long chain of morphisms, we got a map from D home A LM to to home M new L. Yeah, so this whole thing is what we are going to call the composition, call the composition as psi LM. Yeah. There is only one morphism, the rest are isomorphisms. Okay, so what is the property of psi LM? So that psi LM is an iso if M is projective. Okay. Now comes, the more interesting bit. Yeah. Okay, so oh, no, I think before that, maybe I should also remind you of what we are talking about. So originally, I think we said kernel or no, co-kernel of file M is the home. Yeah. Whereas if because we have applied D on that, now co-kernel becomes kernel. So kernel of the new morphism is D of the projective home. So kernel of psi LM is D home LM. Yeah, I think I'm writing correctly. Yeah, D home ALM. Okay, any problems so far?
Sorry, I'm just a bit confused over here. That hom underscore LM, it's only a vector space, no? It's A linear maps from L to M.
Yes, it's a vector space.
So then what does capital D mean for that?
A capital D just on vector spaces, no? It's a duality between vector
Oh, sorry,
spaces, not
it's
blank
hom
A.
key. It's hom key. Okay.
Yeah. Okay. Okay. So now we will just start with this. Yeah. Start with a minimal projective presentation. So which is 0, M, P0, and P1. I'm going to call this F1, this I'm going to call F0, and I'm just going to construct a large diagram and hopefully finish the arguments over there itself. Right. Now, first of all, I'm going to apply D home blank. Just hold on. No, I think I made a mistake. I shouldn't start with minimal projective resolution of this. I have one more step in between. Yeah. So we have been talking about L and M, but how to choose this L? Yeah, in our original formula, we have some N, and we are saying that tau inverse N is going to come into play somehow. Okay, so what I can assume, so assume that N has no non-injective summands. Yeah, so that N is equal to tau L for some L. Yeah, and this is the L that we are going to use. So start with a minimal projective presentation for this L. Yeah, so 0, L, P0, and P1. This is my F1, this is my F0. And now I'm going to apply these two functors. One is D home blank M on this. So D home blank M, because home is left exact and D home blank M will preserve the, no, I think, what am I saying? Yeah, for L, I'm applying in the first component. Yeah, because of D, it will be like this, P1M, then D home P0M. All these homes are over A, I'm not writing them. Then D home LM, and then there will be a 0. On the other hand, what we have is this home M new blank, that is the functor I'm applying on the injective presentation of tau L, minimal injective presentation of tau L. So which is, I'm just applying this. Let me finish writing this. So home P0 new, home M P0 new P0 and home M new L. Okay. So what I was talking about is this, that you apply Nakayama on this. So you will get new P1, new P0, then new F1. And over here, you will get tau L. But tau L is N. Yeah, that we should remember. Tau L was chosen to satisfy this. So on this minimal presentation, we get this. So we know that this bottom row is exact. The top row is exact because we applied a right exact functor. And over here, I will have psi lm over here. Then over here, I have psi p1m. And over here, I have psi p0m. But now let us go back. So psi lm is an isomorphism if m is projective. Did I write it correctly? If L is projective, yeah, not. I want these vertical maps to be isomorphisms. Just hold on. Okay, let me check this. If M is projective, so we are saying M, M, M everywhere. And psi LM is, so the domain. So psi P1M. Can anybody spot something like why are these isomorphisms, the vertical ones?
Sir, I have a doubt.
Yeah.
Somewhere above you wrote that the kernel of psi lm is d home.
Home blank, home like projectively stable LM.
Yes, sir. So if it is like, then is this just 0 d home
No.
lm if like?
No, I think I understand the mistake. Sorry. So when we did this, we dualized everything. When we took this d phi lm, we dualized everything, and therefore the actual result that is written is if L is projective. And therefore, these ones are isomorphisms. This is an isomorphism. This is an isomorphism. Sorry, Riju. Now you can say the question like phi lm is this.
So like we have written that the kernel of this is equal to d home lm. So because this thing is an isomorphism, if L is projective, then is d home lm 0 in that case?
Yes, that is correct. Yeah. No, in both cases it is 0. If either L is projective or M is projective, in both situations you will get it to be 0. But that is not the point. Yeah, we applied the duality, and therefore for psi LM, it is an isomorphism if L is projective. So this is now correct. Yeah, sorry, Riju, you have something more to say? Okay. So these things are isomorphisms. So we can go from here to here as well. And what do we know? That the kernel here, kernel of psi lm, is the required thing. Yeah. So if we extend this exact sequence vertically, then what we require is true. But now look at this. Tau L, nu P1, nu P0. This is an injective resolution. Yeah. This is an injective resolution, like nu P1 is actually the 0th term and nu P0 is the first term of that injective resolution. So therefore, in order to calculate the extension, yeah, so what is ext? What do we want to capture? Ext1 a mn. And I told you that you can also use the injective resolution. So this is going to be this is isomorphic to, I mean, okay, maybe I haven't written the maps here. So these are F1 tilde, F0 tilde. This is F1 bar and F0 bar. So actually, this is isomorphic to kernel of F0 bar quotiented out by image of F1 bar. Okay, so this is the Ext group. So what we have to do, I mean, I'm just going to orally explain what to do. So kernel of F0 bar, which is sitting inside here, from that you go back along the isomorphism psi P0M, then you go here, you will actually see that you land inside kernel of psi LM. So we define a morphism, so define phi morphism from kernel of F0 bar to D home LM, and then you show something, yeah, and prove that image of phi is kernel of psi LM and kernel of phi is image of F1 bar, and then the proof is complete by first isomorphism theorem. So one thing you get here, the kernel is here and the image is this. So there is some verification over here and that completes the proof. Any questions? Okay, so in that case, let's just proceed. Well, Auslander-Reiten formulas have got some interest.
Sorry, so
yeah, sure.
Just one thing, because I'm not sure I can really follow all the details, just general outline.
Yeah.
Is this something that is that has to be seen abstractly, or is it possible to work this out in some example, maybe, or is it amenable to seeing in
try
examples?
To see one example at the end. Yeah.
Okay.
Yeah, we'll try to see one example. I mean, no, I think Isha has put some examples in the tutorial sheet as well. The proofs are abstract. Yeah, I can't help that. We have to like understand it abstractly and like see, I think this sleek theory, that's the slipping in of like this weird connection between Ext and Holmes. I think somebody observed this magic and therefore this theory is in existence. I don't really get a feeling of this. In Auslander-Reiten's Quivers, we can see these things. And I will show you some examples, hopefully. So the first corollary is that if projective dimension of M is at most 1, then X1 Mn is isomorphic to D home of N tau M. So what is the difference here? That we are not considering the projectively stable home. We are saying it's enough to just directly compute the home and take the D. Okay. So how do we prove something like this? Recall, we proved one result yesterday that projective dimension of M is at most 1 if and only if home dA tau M is 0. And also recall that dA, we showed this earlier, dA is simply the direct sum of all the injective modules. So therefore, what we conclude is there is no morphism from N to tau M which factors through injectives. Just because this particular home is 0, so no morphism which factors through injectives lies in there. So therefore, we can just take home bar, the injectively stable home is nothing but normal home. And I mean, why this is interesting? Because I mean, let us look at the note first. If A is hereditary, then the hypothesis of corollary 1 are always satisfied. Projective dimension of anything, any module is at most 1. So therefore, we don't even have to ask for this condition. We just have that extent X is isomorphic to home, D home. And the second corollary, which is also interesting, that if both Mn are indecomposables and N is non-projective, and their projective dimensions and injective dimensions are at most 1, then home tau and tau M is home Nm. Well, I'll tell you the proof, but look at these examples. Yep. These are the examples we computed during the tutorial. So this is A3 with normal, like parallel orientation. So this is the AR quiver. Now we know that all the projectives, they lie here on this chain. The remaining ones are non-projective. So if you want to compute home Nm, like this, and like if this is N and this is M, then home Nm is 0. And similarly, home, I mean, maybe I should write something. If this was my N, then this is my tau N. And maybe I will say this is my M and this is my tau M. So you can see there is symmetry here, translational symmetry, that home Nm is 0 and therefore home tau and tau M is also 0. It's enough to calculate just one of them. Dually, if you say home Mn, then that contains one irreducible map. So therefore dimension is 1 and home tau M tau N is also dimension 1. Same thing can be seen here in the other orientation. Yeah, if this is M, then this is tau M. And this is N, this is tau N. And you can verify these formulas. And how to prove this simple result? Since N is non-projective, then tau inverse tau N is just N. And since this injective dimension and all these criteria are satisfied, so X1 is you transfer this tau from the right-hand side to the left-hand side and you swap the components. So tau inverse tau N, which is just N, and you use again the other direction of this formula, Auslander-Reiten formula, and you get this as a result. So I did not show you the exact computation, but extensions also, let us see. Yeah. So look at extensions here. So if this is my M and this is my N, let me call this M dash. Yeah. This is my M dash. Then please correct me if I'm making a mistake. Like extension, I think the first term, like N comma M dash. Yeah. This is one dimensional, because the middle term is just this M. So this is one dimensional. And if you talk about the home of tau n m, wait, n tau m, right? N tau m, so m dash tau n, which is nothing but home of m dash m dash. And this is, I mean, just it's a simple module. So what is its endomorphism? It's just one-dimensional. And this is also one-dimensional. So this is a simple verification of the Auslander-Reiten formula. I'm not sure whether this very simple example was helpful, but the proof has to be done in a more abstract manner. Well, okay, let's come to this important thing that we are now guaranteeing. Sorry, what am I writing? I thought I clicked on this. Yeah. We are now approaching the existence of AR sequences. So if M is non-projective and decomposable, then there is an AR sequence which ends at M and starts at tau M. This is the consequence of the AR formulas. Yeah, and then there is a dual version that N begins at a non-injective and ends at its tau inverse. What is the idea of the proof? Instead of reading that, if you know a little bit category theory, adjunctions have got units and co-units. And if you set up your adjunction correctly, then unit and co-unit are actually just corresponding to identity maps under certain bijections. The idea is very similar over here. So if M is non-projective, then tau M is indecomposable. Use this bijection. So what are the extensions of M by tau M? Well, that is in bijection with D, the projective home, tau inverse tau M M, but this is because it is non-projective, so tau inverse tau M is just M. So this is D of endomorphism of M. Yeah, so endomorphisms have one particular element, and that is the identity. So whatever corresponds to the identity under this bijection, that is your required almost split extension. A very beautiful idea over here. And of course, like there is a verification that this has left a minimal almost split or this is irreducible. But the idea of the proof is very beautiful from Auslander-Reiten formulas. And the dual version. Yes.
So sorry, just the homs and the ends are with underline, right? That means that they're in the stable category, no?
They are in the stable category. However,
okay, so then I just
yeah, please complete.
No, go ahead. Yeah, please go ahead. Yes.
So if M is non-projective, then identity of M is not going to factor through any projective. So it will survive. It will be a non-zero element.
Okay. No, that was one question. But the second one was that okay, so that is okay, but on the left it's the ordinary X. So there the Yoneda interpretation of X as X1 extension is still valid. It's because that's in an abelian category.
Yes. Yeah, very beautiful idea.
Very nice, yes.
Yeah. Okay, so just one corollary of this result, the existence of this, if M is indecomposable and non-projective, then the projective endomorphisms of M are isomorphic to K. I mean, it is a local ring. Projective endomorphism ring of M is local if and only if the projective endomorphism ring of its translate is local. And in this case, any non-split extension is almost split, with projective thing being isomorphic to K. Okay, so there are certain things to unravel here. See, normally if M is indecomposable, then endomorphism ring is anyway local, which means endomorphism is isomorphic to K. So here we are saying that the same thing happens with the projective endomorphism algebra. And if you have a non-split extension, you just have to figure out that a certain extension is non-split, and then you know for sure that it is almost split. So basically we are saying that the extension group is 2. It only has 2 elements. Okay, so let us look at one example. And
no, actually, that last one is, I think, a little misleading, no? Because
okay.
Because see, for example, extension of Z mod PZ by Z mod PZ in just a billion groups is what? It's Z mod PZ, no?
Okay. No, I can't do these computations on top of my head.
Right.
You can, yeah.
No, I think so. I think the issue is that yes, there are only 2 extensions, but it is, I think, a bit misleading because the X group or the X vector, it's a vector space. No, everything is over K. So,
oh, right.
So it is going to be K. It is just that the zero
sorry.
the zero.
Sorry.
No, I mean what you said is morally correct, but technically the 0 extension is the split one, and all the non-zero ones abstractly they will be equal to the
yes. They will be equivalent to the almost split one. All the non-zero ones. So it is K. Yeah, I'm sorry. I was just thinking about it from a different perspective. Okay, let us look at this example. Yeah, we have enough time to just finish this example. So we are again talking about the Kronecker quiver. Well, for some reason, like I prepared the other half yesterday and this half today. So therefore, A and B are the new notations of the arrows instead of alpha and beta. And the module is again the same, like it is the module corresponding to just the arrow A. And consider this minimal projective presentation of this. Well, in this case, the minimal projective is P1 and then P2. So P1 is this 3-dimensional module, because recall that it is generated by all paths starting at 1. So they are going off in different directions. So k square. And this is our original one. And the kernel is going to be a simple module, and it is also projective. Yeah, which is P2. Okay. So you apply the Nakayama functor at this place, and you will get P2 gets mapped to I2, P1 gets mapped to I1, and F1 is new F1. Well, what it is doing, it's just talking about the second component. Yeah, this map corresponding to B. Yeah, that is the target of that map is where this image is going over here. And so kernel of that is going to be our Auslander-Reiten translate. Okay. So you can compute what is I2. I2 is 3-dimensional again, and it is k square k. So dimension vector 2, 1, and this is k0. And what is mapping to what? So the top one is getting mapped. I think it's the second one. Yeah, I have written the map 0, 1, and so it's the second projection over here. And here you will get back the first the map corresponding to the top row over here. The map corresponding to arrow A. So you get it back. So what you observe is that you started with M, and the tau M that you obtained, the translate is isomorphic to M itself. If you remember, we have computed this example in the tutorial as well. Yeah, there was a cycle in the Auslander-Reiten quiver, starting with this module, the string module associated with vertex A. Okay. Now, since M is non-projective, every non-split extension gives an almost split extension. Yeah, we just saw that corollary of that result. And here is one non-split extension. So k square identity, and then this is one copy mapping to another, one copy of k and mapping to another copy under this. which is actually just a string module. So what's happening? This particular thing is this string module, and the 0 zeros I have just padded it so that you understand where to go. The blue highlighted part is going to this blue highlighted part, and the green highlighted part is mapping onto the green highlighted part and the obvious maps. And this is a non-split extension clearly because these two copies, if it were a split extension, then this map, this thing over here, the arrow corresponding to B would be a 0 map. But since it is non-zero, it is not split, and by the result, it is almost split. So this tells us what that thing, what that particular component, not component, but some part of the Auslander-Reiten quiver should be. Yeah, this is the unique extension of M by itself. So this is the end of Auslander-Reiten theory. Any questions? Okay, so tomorrow we will look at some more, I mean, yeah, there was this classification, yeah, Drost classification, trichotomy. So trichotomy result we'll see. I mean, I will make the concepts of tame, wild more precise. I will try to give you some examples and convince you why wild is wild. And I will also give a partition of tame representation class into domestic and non-domestic, and give you one, like work out one example of a morphism which has infinite factorization, never-ending factorization. So if you have heard of like indecomposable is one side, yeah? Indecomposable means it cannot be decomposed further. Whereas on the other hand side, you have super decomposable module, which means if you factor it, if you write it as a direct sum of 2, then at least one of those summands will further split. And again, at least one of those summands will further split. So that infinite splitting will continue happening. So I will try to give you some similar example in morphisms. Yeah, rather than just modules, I will give you an example of a morphism which has a factorization indexed by rational numbers or dyadic rationals to distinguish between yes, Raghuram?
What you described, it shouldn't be possible for a finite dimensional module, right?
No, it's infinite dimensional. Super decomposables are infinite dimensional. Otherwise, 0 is, no, I mean, yeah, 0, it depends on convention how you see things. But for morphisms, it will be possible between finite dimensional modules. Yeah, and I will do that tomorrow.